Hey, Kale class, we're going to continue on in our 4.1 notes working with integration. And part of this lesson is going to be introducing what a differential equation is. Basically, it's just saying, this is an equation that represents the derivative of some function y. And we spent a lot of time talking about derivatives and that they were slope finders. So to graphically represent all of the slopes that this function could represent, to do that, sometimes they use what's called a slope field, and that's what we have over here. And really what it means is, and maybe you notice all these little line segments here, what they're representing are different slopes depending on where you are on the coordinate plane with the original function y. Okay, so because this is the derivative function, it's giving you all the possible slopes at different x positions. Now, because this derivative is only in terms of x, you'll notice that if the x coordinates are the same, you have all the same looking slopes, right? You can see this is a fairly steep negative slope, and then it's getting a little less steep, still negative, and then as you move along, they're getting less and less steep, and then at a point here in between 1 and 2, it looks like it changes from a negative slope to a positive slope. Now think about that. Here, if I were to put some number between 1 and 2, like 1.5, into this slope finder, if I put 1.5 in here, that gives me a slope of 0, which makes sense in this graph because that's where it's changing from negative to positive, right in between the x coordinates 1 and 2. So that's really what this graph, it's called a slope field, or a vector. Sometimes they call it slope field. I think is the most common name that you're going to see for it. So what they ask us to do here, so it says a differential equation, a point and a slope field are given. So there's a point right there. So the slope field consists of miniature line segments whose slopes are equivalent to the value of the differential equation at each indicated value of x. And that's kind of what I was talking about. For example, over here, if x was -3, I'd have a slope of 2 times -3 minus 3, like -6. So they're trying to draw little tiny line segments that have slopes of -6 right around that area. Okay. These lines give a visual perspective of the slopes of the solutions of the differential equations for various values of c. Now recall this, so when we solve, and we're going to spend more time solving differential equations, but what we do, remember the inverse operation of derivative is antiderivative or integral. So if I wanted to solve this for y instead of derivative of y with respect to x, I would take the integral. I would take the antiderivative of that side, but then I also have to do it to the other side, right? That's really what we're doing. And I don't have all the notation in there like we'd normally have a dx on this side, but in the way we do that is we multiply this dx over here, right? But the main idea is if I take the integral, I'm going to be left with y over here. And if I take the integral here, we had our power rule we could do that with. And so, that would add 1 to this exponent, would be x squared divided by 2. And so the 2 would cancel, I just have x squared. And then the antiderivative of the -3 would become -3x. And then I would put a plus c at the end of this, right? Because I always have to put a plus c. Now, that's kind of where this slope field idea comes in here. Because, really, this parabola, x squared minus 3x plus some constant, it's going to be, a parabola that fits these slopes, but it could be anywhere on this, vertically shifted depending on what the c, if I have to know something specific to figure out exactly what that c is. So what they asked me to do for part A, it says sketch 2 possible solutions to the differential equation, one of which that passes through the given point, that point that they have right there, and then another one we'll just sketch. And then it says use integration to find the particular solution. Okay, so I used integration here. When they say particular solution, they mean exactly what is the equation, and we have to find the c based on this point right here. So here's what they mean by just like sketch. I'll do the first one that doesn't go through that point. We're just kind of following those slopes approximately and sketching, what that parabola would look like as it follows those slopes. And that's not a very good sketch, but I'm not very good at drawing those. But that's kind of an idea there, right? And then another one, if I was following and it goes through that point, might look something like that, right? So same shape, but shifted vertically on the, you could shift it up or down based on whatever c is. Now, since they told us right here, this c value, which appears to have coordinates 2, 3, right? So if I know the coordinates are 2 and 3, then I should be able to figure out what that c value is. So I can just plug in, I can plug in a 3 for y and a 2 for x. and then I can solve for c. So I have 3 equals 4 minus 6 plus c. 4 minus 6, negative 2. I'm going to add that to the 3 and get 5. So when they ask for a particular solution, that means figure out what c is, but in order to do that, they have to tell you, sometimes they call it an initial condition, or but they have to give you a point that's on the actual function. Okay, so then you plug in and figure out the c value. And so my particular solution, x squared, y equals x squared minus 3x and plus 5. And if I were to plug that in and graph that, it would be this parabola that I've drawn up here going through that point. Okay, so that's solving a differential equation. To do it, you take the antiderivative of both sides. That cancels out your derivative of y with respect, leaves you with y, and then on this side, you do your antiderivative. With a plus c, to get the particular solution, use a point that they've given you that's on the actual graph. Okay, all right, example 4. So now they've given us, it's another way of kind of doing a differential equation. They say, hey, this is the second derivative of f of x. And then we kind of need to work our way backward, and we want to solve for what f of x is. So they've given us some information here. We're starting with f double prime of x equals 3. So let's start at that point. We know that f double prime equals 3, right? Now what I'm going to do is I'm going to integrate like I did before, because this is a second derivative. So I'm going to integrate that, and I'm going to integrate this side, and technically I have like a dx on there. But when I take the integral or the antiderivative of a second derivative, now it brings me down to a first derivative. So now that's f prime, and then the integral or antiderivative of constant, that's just going to be 3x, but I have to put plus c with that. Now this is important because we have to find that c. They've given us some information about the first derivative. F prime of 2 is 5. So I have enough information to plug in f prime of 2. I could put a 5 here and then put in a 2 for x, because it's saying when x is 2, the second derivative is, or I'm sorry, the first derivative is 5. So then I can do that. I can put 5 here, right, because that's what I've got, and then that's when x is 2. So 3 times 2 plus c. And then I can solve for c. This is 6. Take that away. I get c equals negative 1. Okay, so now I can start with, I'm going to go up here, my first derivative, f prime, is equal to 3x plus 1. Okay, now I'm going to use this next piece of information so that I can, well, first thing I'm going to do is I'm going to integrate. I'm going to integrate again, so I need to get down to f. I want to get it to f of x. All right, so I'm going to integrate here, and I'm going to integrate this side here, dx. So this is going to take me down. Now I have first derivative, and the integral of that is going to just be the function itself, f of x. Okay, and antiderivative of 3x, the power of 1, so that's going to be 2 divided by 2. It's going to be 3 halves x squared, and the integral of the constant 1 is just going to be 1x, so plus x, and then I have to put a plus c at the end. Okay, now I need to find that c, and I've got this information to use to do it. Okay, so I'm going to put in a 10 here, 3 over 2, and then times 2 squared plus my x is 2 plus c. Okay, and let's see, was that supposed to be minus 1? That's where I messed up. C was supposed to be minus 1, and I put plus 1. My fault. Let's change this. This is supposed to be a minus, and that is, I'm going to make that a minus all the way through. So that was a minus. I just missed it. My c was negative 1 there. So that's minus, and that would change that to a minus 2. Okay. So I've got 2 squared is 4, so that would be 6 when I multiply that out. 6 minus 2 is 4. Okay. So that's 6 minus 2, and so that's 4. And I'm going to subtract that, so I get c equals 6. And so finally then, my solution then is this, with the c being 6, right? So I'm just going to plug that in up there, and I'm just going to erase that and just replace it with a 6. Okay, and this is the solution to the differential equation. So I started with a second derivative, integrated once, found c, and then I was down to a first derivative, so I integrated again, and then use this information to find c, and now I've got my particular solution. Okay? All right. Similar example here, except it's more, in an application setting. And we talked about the relationship between position, velocity, acceleration, where if I take the derivative of position, they use s of t for that, I get a velocity. And if I take the derivative of velocity, I get acceleration. So like the second derivative of position is acceleration. Okay, so here it says, you know, these problems, we've seen problems like this before, but maybe setting them up as far as a differential equation is a little different. So what I want to point out is kind of like what we did in this first one, where, you know, we started with a second derivative of something, and then we integrated twice to bring it to the original function. And that's really what we're going to do here. We're going to start with the fact, because they don't even tell us this, but we know that acceleration due to gravity is negative 32 feet per second squared. So that's what I'm going to start with. That's just a constant acceleration. And so because we're working on Earth, and so that's our, you know, that's our acceleration due to gravity on Earth. So I'm going to start with this second derivative saying that f, in, you know, velocity, they give us some information here. It says a ball is thrown downward from a building so that the downward velocity at 1 second is 76 feet per second. So what I'm saying there is that velocity at time 1 second is negative 76, and I'm putting negative because it's going downward. So that, you know, with vectors, that's important to put the correct sign there. What I'm comparing that to, just so that I think it's going to be easier to just talk about f prime and f double prime. So since velocity is our first derivative of our original function position, I'm going to call that f prime of 1 is negative 76. Okay. Then the other piece of information they give me here is that it's 10 feet, its position, that's s, right? Its position is 10 feet above the ground at 2 seconds. So that means s of 2 is 10 seconds. Position at time 2 seconds is 10. And so f of 2 would be 10. So at 2 seconds, its position is 10. So that's kind of like what they gave me up in this problem, right? They gave me a particular velocity and a time and a particular position and a time, okay? So let's start with integrating what I know, and they didn't say it, but this is implied that acceleration due to gravity is negative 32. So second derivative is negative 32, and we're going to integrate on both sides again, integrate dx. And so that's going to bring me down to the f prime of x on the left side, and this would be negative 32x now plus c. And this is where I need to find my c value. And because, you know, first derivative, velocity is first derivative, and I know f prime of 1 is negative 76, so I can put negative 76, and then I can put, that's at 1 second there, plus c. And so I get negative 32 equals, you know, negative 32 plus c equals negative 76, and if I add the 32 there, I'm going to get a negative 44 when I solve that for c. Okay, so now I'm going to come back here. I'm going to rewrite this as f prime of x in my particular velocity equation, or first derivative equation, is going to be this. It'll be negative 32x minus 44. But now I need to continue working my way back and get that position function, because the question is, what's the ball's initial velocity? And so I should refer to this. You know, this is our general form for any, you know, object that's falling or, you know, follows vertical motion. And that's one that's that we kind of have to be familiar with. But the initial velocity is going to be this coefficient on my position function, and initial height will be the last constant there. Okay, so let's integrate again. So we're going to integrate this side and integrate this side with respect to x. Okay, so that's going to bring me down to my f of x function, which is my position function. And here, if I add an exponent here, that's going to be x squared. I'll divide by 2, so that's going to be my negative 16x squared, which is looking like it should. You know, x instead of t, it doesn't matter. And then minus 44t, and then plus c again. We have, and that c is going to be our starting position, but we should be able to figure that out from this information now, right? So at time 2, my position was 10, or f of 2 would be 10, so I'm going to put a 10 here, and that was when x was 2. Okay, and so that's going to be 4 times 16 equals negative 64, and this is going to be minus 88 plus c, and so negative 64 plus 88, what's that, 152, negative 152 plus c equals 10. I'm going to add that over. I'm going to get 162. So that's going to be my initial position. That'll be my initial height. So I'm going to take this 162. I'm going to plug it in up here. Okay, erase that, 162. Okay, so now I've got my equations all figured out. I've got right here, this is my my position function that follows right here, and now I can easily answer these questions. What's the ball's initial velocity? That's the -44. Okay, and then what's the initial? How tall is the building? Meaning, what's its initial position? That would be the 162. Okay, so for part A, I know negative 44 feet per second. My answer there, and then because that's right here. And then for part B, initial position is my answer for that. The building is 162 feet. Okay? So that's solving some differential equations. Starting with the second derivative, integrate twice, and then plugging in to find those C values as you go based on some given information. Okay, last two examples. These will be quick. If you recall when we did derivatives of e to the x, that was a real easy one. Derivative of e to the x is e to the x. Well, that makes it pretty simple that the antiderivative of e to the x is also e to the x, but we put a plus c at the end, right? So in this example 6 part A, let's pull that 5 out of there, and then I've got 5 times the integral of e to the x, so that's just going to be 5 e to the x plus c. That's all you got for that one. Pretty straightforward. Now, when you had a different base other than e, there was an extra step on that when you did the derivative. If I had the derivative of a to the x, it was still a to the x, but then times ln of, oh, I put 2 there. I should have, ln of a, whatever that a is. I was thinking 2 to the x when I did it. ln of a, you have to multiply by that, okay? So when we do our integral, it's still going to be a to the x plus c, but then instead of multiplying by ln of a, you have to divide by ln of a, all right? So in other words, with this, it's going to be 6 to the x, but we have to divide that by ln of 6 and then tack our plus c on there. Okay, that's it. That's everything for the first section.